Good morning. Welcome to day 2 of the RQS Summer School. We have yet another day of exciting lectures ahead of us. Our first speaker is A.Darmawan, who is going to introduce us to tensor networks and tell us more about how they're used in quantum error correction. Andrew.
Okay, thank you very much. So good morning, everyone, and thanks very much to the organizers for putting on this nice conference and giving me a chance to give a lecture. So my name's A.Darmawan. I'm assistant professor at Kyoto University, and the topic for my lecture is going to be tensor networks, an introduction to tensor networks with applications to quantum error correction. So on the tensor network side, I know we have a very diverse, broad audience here, so I'm not going to assume anyone has any prior knowledge of tensor networks. I'm going to start from the very basics. And on the quantum error correction side, it's also going to be very basic. I mean, the knowledge that I'm going to assume is already well covered by Annie's talk yesterday. So yeah, to start with, so I'm basically separating this lecture into I guess two main sections. The first part is really to just go over the basics of tensor networks, the main concepts, and then I'm going to go through like a basic tensor network algorithm called matrix product state compression. So that's going to be, I think, roughly the first half of the talk. The second half of the talk is going to be applications in quantum error correction. So like I've listed a few applications here. Like each section is going to be kind of a self-contained thing. So if you fall asleep during, say, the first one, it doesn't. If you wake up for the second one, it should still be more or less comprehensible. So one thing I wanted to say is that I do very much appreciate questions, so please at any time don't hesitate to put your hand up and get the mic and ask a question. Just like for me, I personally find it a bit difficult to just talk continuously for like 2 hours straight. Okay, so what's the idea of tensor networks? The idea of tensor networks is that we want to decompose complex objects, things like quantum mechanical wave functions, into like smaller, more manageable pieces, like building blocks. Something like breaking something down into Lego blocks. The idea is that by breaking these things down in this way, you can get efficient representations of many different things that we're interested in. So not only can you represent states, you can also represent things like operators, quantum circuits, partition functions, and other things. So why should you study tensor networks? Well, there's a few reasons for this. One of this, maybe the main one is that tensor networks form the foundation of a variety of very powerful numerical methods for studying quantum many-body systems. A famous one is, for instance, DMRG, but like there are hundreds of papers published every year on different applications of tensor network numerical methods. So as I mentioned, you can represent many different things in quantum many-body physics as tensor networks, things like states and operators. And the description as a tensor network really provides a very concrete description of these things. Like by seeing the tensor network, you can really see like how to calculate those things explicitly. And because tensor networks can represent so many different things, it represents kind of a language that is shared among different areas of quantum physics. So things like condensed matter physics, high energy physics. If you understand the language of tensor networks, you can talk to people and at least grasp concepts in a variety of different fields, quantum physics. And maybe, yeah, one of the nicer things about tensor networks is that they're easy to they are human comprehensible. So you have a nice graphical picture of these things, which allows us to use our intuition to gain an understanding of these different objects in quantum physics. Okay, so now I'm going to move on to some handwritten notes. Okay, so these are some handwritten notes I've converted into like a slide size. So I hope you don't mind. I hope you don't mind that these are a little bit rough around the edges, but I think they should do. So in this section, I'm going to go over the basic concepts, the definitions in tensor networks, and explain how you can use them to do certain types of calculations. Okay, so firstly, what is a tensor? A tensor is just a multi-index array of complex numbers. So maybe the most familiar type of tensor would be something like a matrix. A matrix is a tensor with two indices. And the way you draw it in this tensor network graphical representation is as a box with an incoming leg, with a leg for each index. So a matrix is just a box with two legs, a vector which you can regard as a tensor with one index or a box with one leg. And then, of course, you can generalize this to tensors with an arbitrary number of indices, an arbitrary number of legs. So one important concept is the idea of the bond dimension. So we say that the size of an index is basically, we say that's the bond dimension of that index, or the dimension of an index. This would be like analogous to the number of rows or columns in a matrix. And then it's clear that the total number of entries in a tensor is just the product of the bond dimensions of all of its indices. Okay. So the main operation that we have in tensor networks is tensor contraction. And this is indicated graphically by when you have a pair of tensors that are connected by an edge, and it means you contract the index corresponding to that edge. And by contraction, I mean you sum over that index. So the most familiar example of this would be something like matrix multiplication. Okay, so I'm sure you're all familiar with matrix multiplication. The way you would illustrate this graphically is just, you just have the two tensors corresponding to your matrices, and you join the index that gets summed over. So tensor contraction is basically just a generalization of matrix multiplication. And you can imagine, beyond just simple matrix multiplication, you can imagine more complicated contractions like what I've illustrated here, where every time you have an edge connecting two tensors, you just imagine summing over that index. So the result of a contraction like this is always itself a tensor, and the number of indices on that resulting tensor is going to be the number of uncontracted indices. Yeah?
Is it fair to say that tensor contraction is really just a restatement of Einstein's summation notation?
Yeah, I think that's fair enough. Yeah. So yeah, you can. So the number of indices on your resulting tensor is just the number of uncontracted indices in the tensor network. So in this case, in this particular example I've drawn here, there's like one uncontracted index. just like when you're multiplying matrices together, you have to make sure that the indices have the right dimensions. Like you can only contract indices that have the same dimensions. And so as I said, the resulting, the output of a tensor contraction is a tensor, and if there are no uncontracted indices, the result will be like a no-index tensor or a scalar, just a number. Okay, so how do you actually calculate a tensor contraction in practice? So there's actually, there's not one way to do it, but maybe the most common way is to do the contraction pairwise. But by that I mean you contract tensors pairwise together until all of them are contracted. So if we look at this example, one way you can evaluate this tensor contraction is first you contract this V and the A tensor together to get this E tensor. Then you get this kind of reduced tensor network here. Then you can contract the E and the C tensor together pairwise to get this F tensor, what I've called F. And then finally contracting the F and the B tensor together to get the D, to get this D tensor. So, so one thing is it doesn't actually matter what, like in terms of the result that you get, it doesn't matter which order you contract the tensors together. Like whether you contracted CB first or VA first, you'll get the same answer, although it does affect the computational time, and it can affect it significantly. Maybe a simple way to see this is like if you have something like a matrix times a vector. There are basically two orders in which you can do this. You can multiply the matrix by the vector first, and then the resulting, take the remaining matrix and multiply that by the resulting vector. Or you can multiply the two matrices together and then multiply that resulting matrix to the vector. But matrix multiplication is going to be slower than matrix vector multiplication. So you can see that these two things are going to take a different runtime. One of the tricky things is actually working out what the best order to contract your tensor network is. And actually trying to find the optimal contraction order is a hard problem. I think it's NP hard or something like that. Okay, so maybe the most well-known application of tensor network methods is to represent, oh yeah? Oh, did you want to get the mic?
Is the double bond dimension the product of the two bonds?
So yes, so when you have this bond here, is this what you're doing?
Sorry, can you repeat it?
Oh.
Is the double bond dimension the product of the two bonds?
Yes, that's right. So you can always like flatten, like when you have two indices coming out of a tensor, you can flatten that into a single index which has a bond dimension which is the product of the bond dimensions of each individual bond. Yeah.
So I wanted to ask, sorry, is the assumption that these are real or complex numbers?
So yeah, it can be either. Oh, could you wait for the mic?
Sorry, just to say, when we ask questions, just wait for the mic just because it's recording. So any of your questions, then we can pick up on audio.
So with that, you can only work things that commute with each other, I guess.
Commute?
Yeah, like the order doesn't matter to the result.
That's right. The order, oh, are you saying like in terms of the entries of the tensors, they have to be?
I guess in quantum systems, there are always like operators that does not commute with each other. So when you flip the order, it does change the result.
So I think when you're talking about changing the order, in your sense?
In multiplications, right? So.
Yeah, like if you were to switch the order of multiplication of matrices or something like that, that would correspond to a different network. Yeah. So I mean, if you had the same network, it doesn't matter what order you contract them in. Yeah. Okay, so yeah, I guess the most well-known application of tensor networks is to describe quantum many-body states. So as we know, like a general state of like n qubits can be expressed in a basis, as expanded in a basis, like in a local basis like this. So this coefficient tensor, it has, you can regard this as a tensor with basically n indices. So if you have like qubits, then the number of entries in this tensor is just going to be d to the n. So it's clearly not an efficient description in terms of n. So the idea of tensor network descriptions of quantum many-body states is to re-express this coefficient tensor as a more efficient contraction, or in a more efficient way as the contraction of smaller building blocks. So for most of this talk, I'm going to consider a particular type of tensor network state. It's called a matrix product state. And it's where you rewrite this tensor of coefficients as the contraction of a one-dimensional chain of tensors, like so. So in terms of terminology, we regard the indices that correspond to the physical degrees of freedom as physical indices. And these bonds connecting the tensors we refer to as virtual indices. So it turns out that this is, if you don't put any constraints on the dimension of this bond connecting these tensors, then you can actually represent arbitrary states. Although to represent arbitrary states, in general, you're going to need a bond dimension that grows exponentially with the system size. So that's not necessarily an efficient representation of a quantum state. But usually when people talk about matrix product states, they think about constraining to the particular class of states where this bond dimension is fixed and independent of the system size. And in this case, we do have an efficient representation of the state. So, I mean, the way to see this is you just count the number of parameters that you have to describe such a tensor network. So if you look at a single tensor like this A tensor, the number of entries in it is just the product of the bond dimensions of its indices. When in this case, it's going to be d, the physical dimension, times the bond dimension squared. And so the total number of parameters in this to describe this entire state is going to be upper bounded by n times d squared. So you have a number of parameters that scales only linearly with the system size, as opposed to exponentially for describing a general state, a general coefficient tensor. So what you can see, what is clear is that if you restrict to a fixed bond dimension, a constant bond dimension in the system size, then you're clearly not going to be able to represent arbitrary quantum states. But the idea is that you can still represent a large number of states of interest, which might be physically relevant. Yes, and we'll see a bit later that the types of states that you can represent are states with a small amount of entanglement. Entanglement is essentially, like a bounded entanglement is the constraint that these types of states have. Yeah? Oh, maybe do you have, oh, yeah.
Can you say again what the power of the bond was d to the power of 2?
Why it's d to the 2? So, I mean, every tensor like this has two incoming, it has two virtual legs and one physical leg. So because there's two virtual legs, you get a d square factor. Yeah. So it's a 3-index tensor. Yeah. Okay, thanks for the question.
Another question here.
Yeah.
So just to clarify something you said, make sure I got that right. So you're saying the graphic representation you drew with the chain of A1 through AN, if we didn't constrain the virtual bond dimension, we would be able to represent any state?
That's right, yes.
But so the interesting ones we care about will be the MPSs in which we do have a constraint on the bond dimension.
Yeah, so the ones where we can actually run practical algorithms and stuff have like a lobe, a small bond dimension. Yeah.
Okay. And then a follow-up to the prior question about like commutivity.
Yeah.
So if you have like two square matrices A and B,
Yeah.
how would the graphical representation of A times B look different from B times A?
Yeah, so, okay. Maybe I can draw it on the board. So this would be A times V. V times A would look like, let's see, I guess it would look like this. So you've connected different indices together.
Okay, I see.
Yeah. Any other questions?
I have a question here.
Okay, sure.
Yeah, so if I had periodic boundary conditions in my system, would the representation have a connection between the first and the last?
Oh, yes, that's right.
Okay.
So in this case, we have open boundary conditions.
Okay.
Although, yeah, people commonly consider the periodic boundary case where you have it's essentially a trace, so like an extra bond that goes around like that. Yeah.
Thank you.
So this MPS represents 1D entanglement.
That's
if
right.
you had, let's say, like a bond to next nearest neighbors, how much information do you gain by having that ability of connection?
So if you just had next nearest neighbors, well, in that case, it would still be an MPS because you can essentially propagate that long-range bond through the middle tensor. I mean, you'll have a higher bond dimension, but it's still a constant with system size. Yeah, to go beyond MPS, you would have kind of like an extensive number of connections between the different sides of the chain. Yeah. Mm-hmm.
Actually, that just sparked another question then. So like, it seems like the information between how entangled A1 and A3 are is like kind of mediated by A2.
Yeah.
But then like, what if you say, for example, you have like a bunch of bell pairs, but like the first two are in a bell pair, and then like the outer two are in a bell pair, and like outer two are in a bell pair. Like each thing's only entangled with one other thing. But now it seems like to figure out how entangled two things are, you have to kind of be mediated by all these things in between it.
That's right, yeah.
Is that like actually true, or is there like a simpler way to?
So, I mean, are you thinking of like, I'm just trying to picture this. You have a bell pair between like two neighbors?
Yeah, let's say like 3, 4 are a bell pair,
yeah.
and then like 2, 5 are a bell
Yeah,
pair,
yeah.
and then 1, 6 are a bell pair.
Yeah.
Then like if you have to do the entanglement kind of mediated through the neighbors, then it looks like it'd be pretty complicated to see how A1 and A6 are entangled, even though they have like a really simple entanglement structure.
Yeah.
So is there like a simpler way to see that from the MPS, or is that just a limit to MPSs?
So, I mean, the way you would represent that is in an MPS is that you would have like because like on a particular bipartition, you have quite a lot of entanglement crossing, right? So, so you're thinking, let me just draw the picture. So you have a bell pair like this, and then you have another bell pair like this, right? Is this what yeah, that kind of thing. And you want to represent that as an MPS. Yeah, so I guess you would, oops. Okay, so because this bond has like multiple bell pairs crossing it, it's going to have a higher bond dimension. It's going to have, well, if these are qubit bell states, it's going to have a bond dimension of 8. And this one has 2 crossing it, so you're going to have a bond dimension of 4. And this is going to have a bond dimension of 2. So yeah, you can somehow incorporate this longer range entanglement into the MPS by having a higher bond dimensions in certain places. Does that help?
Sorry, the MPS there kind of looks like a Haar random state. No, like is it? But that looks like that's a very different state from Haar random state. But from the MPS, it looks like the same thing.
So I don't see how this looks like a Haar random state.
Like I guess the entanglement is growing as like.
Yeah, so the entanglement is growing as you go into the middle. Yeah.
Like the volume. Okay, never mind. I see.
Okay. Right. Okay, so I mean, so not only do you have like an efficient representation of the state, you can also calculate things using MPS more efficiently than if you just had some big coefficient tensor representing your state. An example of this would be like if you wanted to calculate local expectation values. So just say we had an MPS like this, and we wanted to calculate the expectation value of this operator B on side J, say, like this. So, I mean, the way you would operate on the matrix product state with this Bj is essentially to just contract the B tensor onto site J. Yeah, then to compute the expectation value, you would just contract, you would take this inner product. And in the tensor network language, what this looks like is essentially joining the physical indices together between this state and its complex conjugate, its matrix product state. Then you can evaluate this expectation value simply by multiplying matrices together. So, I mean, what you would do first is you would contract pairs of tensors together, or in this case, 3 tensors together vertically, and then you get a chain of tensors like this. Because we have constant bond dimension, this is just a multiplication of matrices capped off at each end by a vector. And the matrices are of constant size, like a bounded size, independent of the system size. So we can use this matrix product state picture to calculate local expectation values efficiently. Okay. So what happens if you consider like the time evolution of a matrix product state? So I'm going to consider the situation where you apply some 2-qubit gates to your matrix product state. So like everything, you can represent a 2-qubit gate as a tensor. It would look like this. You can also split this tensor up into a contraction of 2 tensors. So I'll explain a little bit later how you can do this using the singular value decomposition. But for now, yeah, just trust me that we can split 2-qubit gates up in this way as contractions of 2 tensors like this. Then in order to represent applying that gate to your state, you just contract these tensors corresponding to this 2-qubit gate to your matrix product state. So yeah, in this case, what I've done is I've contracted the 2-qubit gate I've applied the 2-qubit gate to sites 1 and 2, and then separately to 3 and 4, and so forth. So what you can do then is you can contract these down. So pairwise contract in the vertical direction. What you'll get then is essentially an increase in the bond dimension. So these bonds originally between the two originally between the two tensors representing the gate are now also connecting the tensors of the matrix product state. Essentially, this corresponds to an increase in the bond dimension. So what you find is that if you just keep applying 2-qubit gates in this way, then the bond dimension of your matrix product state is going to increase, and it's going to increase exponentially with the depth of the circuit. And this is potentially a problem because, I mean, if the bond dimension is increasing exponentially, you might no longer have an efficient representation of the state. But fortunately, there are some tricks to overcome this. Namely, we can reduce the bond dimension of your state by compressing it. And I'm going to talk about how we can compress tensor networks next. Yes?
Thanks a lot. So you showed how you can represent a 2-qubit gate as a tensor network, but I mean, often there's things like, for example, if you want to do constant depth preparation of GHZ states, it's really useful to start from tensor networks and get the circuit from that. Can you remind me how the opposite ends up going, how you can go from a tensor network for like an MPS and then translate that to a quantum circuit?
I think that's, yes, I know people do that, but that's not so trivial. So, I mean, I can't tell you off the top of my head.
Okay, cool, thank you.
Yeah.
And what about the case if we have gates that have, say, like bounded Schmidt rank or things like that? Could you get that the bond dimension won't increase as rapidly?
So if a gate has, yeah, so I mean, I think what that basically corresponds to is a change in this bond dimension here. But no matter what the bond dimension, unless if it's 2 or greater, you're still going to have an exponential increase in the bond dimension as you increase the depth of your circuit. Yeah. Oh, yeah? Okay.
Hello. So does it matter whether we contract from the left or the right? So will the answer be same, or we will get different answers?
Whether you contract from the left or the right?
Yes.
Yeah, so it doesn't matter, no.
Thank you.
The order will not affect the final answer. Although, as I mentioned before, the runtime can depend a lot, like the time it takes to do the contraction or the number of operations you need to do the contraction. Matters a lot, depends a lot on the order in which you contract things.
Thank you.
I think there's a...
You can go ahead and ask it.
Yeah.
So if I have a product state, do I understand correctly that I can represent it with bond dimension 0?
1. One, yeah.
If I have 2 product states,
Mm-hmm.
I get some superposition, that would be an entangled state.
That's right.
How does this MPS representation change? I think like the sum could be entangled, but also,
Yeah.
So that's like non.
So I think, yeah, if you had a sum of 2 orthogonal product states, well, the bond dimension will be bounded by 2. And I think this is the general rule is that if you have 2 MPS with bond dimensions D1 and D2, and you take a superposition, then the bond dimension of the resulting state will be bounded by D1 plus D2.
So the bond dimension is bounded by like some Schmidt rank?
Yes, that's right. Yeah. and I'll get to that soon, that there is a close connection between the Schmidt rank and the bond dimension. Yeah.
So what is the optimal way to contract a tensor? Or
A tensor network? So like in general, it's a hard problem. So like if I just give you some graph representing a tensor network and you know all the bond dimensions, and I ask like what's the contraction pattern that will have the lowest the lowest memory cost and runtime cost. That's an NP hard problem to optimize.
What if it is an MPS? Is it known there?
Well, it depends what you want to do with the MPS, I guess. Okay. So like what part do you want to contract? Like usually, so for instance, if you're computing an expectation value or something like this, and you have to contract, 2 MPS together, it makes sense to contract in the vertical direction first and then contract horizontally. So, I mean, in some cases you can kind of see what the optimal contraction pattern is, but sometimes it's impossible to know. Yeah. Okay, good. Thanks for all the questions. Let's keep going. Okay, so I'm going to talk about, so as I mentioned, the bond dimension in general is going to increase exponentially with the depth of the circuit applied to an MPS. So we have to think of some ways in which we can compress an MPS to get a more compact, efficient description. And the way I'm going to, so I mean, the rest of this, let's see, how much time do I have? Okay, hopefully I'll be able to get through this, but I'm going to talk about how we can do this type of compression. And at the heart of this compression is the singular value decomposition. So this is something that you can, I mean, you're probably all familiar with this. It's something you can apply to an arbitrary matrix. So just say we have an n by n matrix, Aij. The idea is that you can always rewrite that as the product of a unitary matrix times a diagonal positive matrix times another unitary matrix. And without loss of generality, you can always regard the entries in this diagonal matrix to be decreasing or non-increasing. So you have the first entry is the largest, and second entry is the second largest, and so on. So yeah, to draw this graphically, it would look something like this. And you can apply this singular value decomposition not only to matrices with 2 indices, but to any tensor which has 2 or more indices. But you have to choose which indices are going to correspond to the rows and which ones are going to correspond to the column. So you essentially flatten some of the indices into a single index and get a matrix. And then you do the singular value decomposition of that resulting matrix. And then you can unflatten those indices again. So this is how you can obtain this description of the 2-qubit gate as a contraction of 2 tensors like this. Okay, so singular value decomposition basically gives you a way of approximating matrices by matrices of a lower rank. So the idea is that, as I mentioned, you imagine that the singular values, the diagonal entries of this diagonal matrix are decreasing. And the idea is that you basically make a the idea of the approximation is that you make a truncation so that you basically, beyond a certain number of, you basically set the small values of this, say the first, all of the entries of this after, say, the first chi singular values to 0. So you'll get an approximation like this, just by setting all but the first chi singular values to 0. And whether or not this is a good approximation is just going to depend on how big those values were that you set to 0. If they're already close to 0, it might be a good approximation. Otherwise, it may not be a good approximation. And this gives you a compression of the matrix. So it means that basically, rather than storing this whole unitary matrix, or these whole unitary matrix, you only have to store the columns or rows of that matrix corresponding to the non-zero singular values. And you only have to store, so while we originally had like an n by m matrix, the compressed version will, for this U, the compressed version will have an n by chi matrix, where chi might be a lot smaller than m. Okay, so I mean, for people who like seeing things graphically, you can think of the compression kind of like this. So you have your matrix, and you want to approximate it using the singular value decomposition. The idea is that you basically set all but the first chi singular values to 0, and then to represent this matrix, you only have to keep track of the first chi columns of U and the first chi rows of V. Okay. So, I mean, this is a very useful thing. It can be like lots of types of data can be represented as matrices. So like you can imagine an image, for example. It's a simple way to do image compression by just truncating singular values. But it's also a natural way to compress bipartite quantum states. So imagine we have a quantum state, two subsystems, A and B. And you can imagine that like the local dimension of A and B can be quite large, for example. So to describe such a state in general, you just need to have this coefficient tensor, this Cij. You can apply the singular value decomposition directly to this Cij. And what you get after absorbing these unitaries into, after contracting this unitary with these basis elements to get these states, is essentially a form of the state that looks like this, where you have a summation over singular values multiplied by tensor products of orthogonal sets of states like this. So this is called the Schmidt decomposition of a state. And we can apply the idea of compressing using the singular value decomposition to compress this description of the state. So again, we set, to do this compression, we'll just set all of the singular values after the first chi singular values to 0. And then you'll get an approximation of the state, which requires a smaller, which can be described using fewer parameters. So these orthogonal states now can be represented using these truncated matrices. Okay. Any questions about this? Okay. Yep. Oh, so I'm going to get to that, yes. For sure.
How do you, I guess, choose chi? Like, what if a lot of the singular values are very close to each other?
So Yeah, I mean, you're free to choose chi to be whatever you want, but like the resulting approximation to the state may not be good. So basically you want to set chi such that the singular values that you set to 0 are already close to 0. So you're not losing too much information. If you're setting a bunch of singular values to 0 that that are large, then you'll get some large truncation error. Yeah. Okay. Okay, so this Schmidt decomposition is provides a very clear way to describe bipart entanglement. So, I mean, this is the Schmidt decomposition, which I wrote before, where these are orthogonal sets of states, orthonormal sets of states. So we say the number of non-zero singular values, or number of non-zero Schmidt values, is the Schmidt rank. And for a state which has, say, D, Schmidt rank of D, you can put some bounds on the entanglement, the von Neumann entanglement entropy of that state between subsystems A and B. It's going to be bounded by log D, essentially. Right. So what we can see from an MPS is that the bond dimension of the MPS actually bounds the Schmidt rank. So for MPS of bond dimension D, the Schmidt rank is bounded by D. And so the entanglement entropy between any two halves, any bipartition of the chain, is going to be bounded by log D. So this tells us something about the entanglement in matrix product states. So if we keep D to be system size independent, what it means is that no matter how big your MPS, the entanglement between any two, any bipartition of the chain is going to be bounded. And furthermore, if you want to describe something, if you want an MPS with, say, a growing bond dimension, you need the bond dimension to grow quite quickly in order to say, to describe, say, linearly growing entanglement entropy, because the entanglement entropy is log D. So, I mean, the basic upshot of this is that matrix product states, where you have small d, represent states with small amount of entanglement. Okay. All right, so now okay, I'll try and get through this kind of quickly. The idea of the next algorithm, so I'm going to talk about a very useful algorithm that you can perform using the MPS description of a state, which is called MPS compression. The idea is that you have an MPS with a certain bond dimension, and you want to approximate that by another MPS with a lower bond dimension. Okay, and the idea, the way that we do this is we put the matrix product state in a certain form. It's called the canonical form, which essentially corresponds to like a Schmidt decomposition of your matrix product state, where you can read off the singular values, the Schmidt values directly. Okay, and the key tool for this algorithm is the SVD, which we apply sequentially. Okay, so just say we have an MPS, just some arbitrary MPS like this, and just say it has bond dimension D. What we can do is we can put it in a certain form by repeatedly applying singular value decompositions to the tensors. So Basically, you start from the left-hand side, this A1. You do the singular value decomposition. You get this unitary, diagonal unitary decomposition. You take the diagonal part and the second unitary, and you contract that with the A2, the second tensor in the line. You get a new A2. Then you do the same thing again to this tensor. So in this case, you regard these as the input. You sort of do a decomposition regarding these as the left index and this as the right index of the matrix. Okay, so then again you get a unitary multiplied by diagonal by unitary. You multiply these two into the next tensor, and then you repeat. And you repeat, just say we want to compress a particular bond. Say we want to compress bond K, so like after the kth tensor. We repeat this procedure up until bond K. So then we have the matrix product state in a form where you have a whole set of unitaries to the left of bond K. All right. And then you do the same thing coming from the right. So you start from the right-hand side, do SVD, keep the unitary, and then absorb the other two into the next tensor, and so on. And what you'll have in the end is something that looks like this. You'll have unitaries on the left of your bond K, unitaries on the right of bond K, and then you'll have one matrix of singular values on bond K, like this. Right. So this is sometimes called the canonical form of an MPS. Okay. And it turns out that this is basically a Schmidt decomposition of your matrix product state. So this state can essentially be written like this, as a Schmidt decomposition, where this is a set of orthonormal vectors, and this is a set of orthonormal vectors. Where these sets of states, like these psi A, correspond to the contractions of these unitary tensors to the left of the bond, and these tensors, these states correspond to the contraction of the unitary tensors to the right of the bond. Given the fact that these are the orthonormality comes from the fact that these are all unitaries. This is easy. The orthonormality condition is quite easy to check. So now we wanted to compress this particular bond. We can just do it in the same way that we did all the other compressions before. So you just set all but the first chi singular values to 0. And then you reshape the tensors to the left and right to only keep the information that corresponds to the singular values that are non-zero. Okay, and so essentially, once you've done that, you've basically obtained a new matrix product state which approximates the original one, but the bond dimension of bond K has been decreased from D to chi. And the approximation comes from discarding small Schmidt values or small singular values. Okay, so since the Schmidt rank is a way to quantify entanglement, this approximation is only going to be good if the entanglement between the two parts of the chain, between to the left of bond K and to the right of bond K, is small, is small. So, I mean, the way I've described it is not the most efficient way you would do it in practice if you wanted to. So what you would probably want to do is you want to decrease all of the bonds decrease the bond dimension of all of the bonds in your matrix product state. I just talked about if you wanted to compress a single bond, the way you would decrease all of them is you'd essentially do a sweep from right to left, repeating the same procedure that I mentioned. And there are some various tweaks you can do to the method to improve the efficiency of the method. If you're interested in reading up, there's this good reference. Okay, so this gives us basically a way in which we can perform time evolution or simulate time evolution using MPS. So as I mentioned, applying 2-qubit gates is going to increase the bond dimension. If you don't do anything, the bond dimension is just going to increase exponentially. But by occasionally applying this bond dimension compression and assuming that the entanglement doesn't grow too much, you can do an efficient simulation of the matrix product state. Okay, so all right, that's perfect timing. So I'll finish the first half of the talk here, and for the next part, I'm just going to talk about applications. Do we have any questions just before I finish? Okay, if not, then yeah, see you in half an hour.
We are on break. Be back at 10:30.